Lesson 4, the objective function and optimal solutions. And this is really the last little bit of theory for Chapter 15. The learning intention for this is that students will be able to identify the objective function of a linear programming problem and will be able to determine the optimal solution. Success criteria: if you can use the corner point and sliding line methods to find the optimal solutions to a linear programming problem, then you know what you need to know. So what is the objective function? We talked about this briefly in Lesson 3, but we'll get into a little bit more detail now. Simply put, it's a mathematical relationship between our two decision variables, that being our x and our y value. The goal of linear programming is to give the best value, which is usually going to be the smallest or the largest possible value of the objective function. So we're trying to make whatever this relationship is between x and y as big or as small as possible. The optimal solution, that is the values of x and y that give us this best possible result. The values of x and y that gives the maximum or minimum solution to whatever this objective function is. Of course, a restriction here is that because we have all of these inequalities, x and y must lie within the feasible region. So just as a quick example, if the objective function was I'm trying to make x plus y as big as possible, well, I can't just pick any value of x and any value of y. I've got to choose x's and y's that lie within the feasible region. So of all the points in that feasible region, what's going to give me the best or the biggest value of x plus y? So it has to satisfy all those constraints. So how do we go about finding the optimal solution? Because in a feasible region, so that polygon, that shape that we have, whatever it might look like, there are an infinite number of choices. Millions upon millions. You could never count all of them. So hopefully we don't have to check all of the solutions. And we don't. The optimal solution, whether it's a maximum or a minimum, lies on one of what we call the corner points of the feasible region, which, another word for that, is required region, we've seen that before, and a solution polygon. So the corner point method, we need to determine the points that are in the corners of the solution polygon. So any points that are at corners, I'll just change this side a little bit, bring it out like that. There's another corner. So we need to figure out what those points are. They are the points of intersection of any pair of constraints. This guy here is the point of intersection of that line and that line. We know how to find points of intersection, so we should be able to find our corner points. We substitute the x and y values of our corner point into the objective function, and we'll do that for each of the corner points. Whichever corner point gives us the best value, so again, maximum or minimum depending on the context, that is our optimal solution. So we'll plug in each one of these points here. Whichever one gives us the best value for this objective function, that's our best solution. So to visualize this, this is a problem that we looked at. This is a feasible region that we looked at in Lesson 3. So one of the corner points of this solution polygon here, this feasible region, will provide an optimal solution. So there's 1, 2, got to be careful, there's a third one here that's easy to miss, 4, and 5. So it's wherever two of the constraints intersect. So let's look at this example in a little bit more detail to see how this actually works. Because that's really all the theory it is. It's just a matter now of going through an example. If you don't remember this example, go back to your notes from Lesson 3. This was creating videos for Tempest Mathematics. So we had a list of all of these constraints. They're all graphed here. And now we're told, this feasible region then, that's all the values that satisfy these constraints about the number of videos. And we're told that lesson videos are sold for, $250, and example videos are sold for $100. So just change that there to $250, and example videos are sold for $100. How many videos should be made each week in order to make the most money? So, out of all of these points in here, which X represents the lesson videos, Y represents the example videos, which one of these values is going to give me the best profit, the most profit? So, let's have a look at this. First of all, let's figure out the objective function. So the objective function is that thing that we're trying to make as big as possible. That's the profit, the total amount of money. I want to make as much money as I can selling these videos. I wish. So the money that's made from the lesson videos, that's $250 per video. So the total amount of money, if I sell one lesson video, that's $250. If I sell 2 lesson videos, that's $500, and so on. So the money that's made from the lesson videos is 250x. And the money made from the example videos is 100y. Again, y as our decision variable, that is the number of example videos. X was the number of lesson videos. So the total amount of money that I'm making is 250x plus 100y. This is the objective function, and we are looking to maximize that function. So what values of x and y can make this as big as possible? So there's our constraints, there's our objective function. Let's start figuring this out. Got my corner points. 1, 2, 3, 4, 5. So I need to figure out here, what are the values of these corner points? Where are they? And which of the corner points will give us the highest value for this objective function? So rather than having to check all of these points, this point here, this point here, this point here, this point here, I don't have to worry about those. Because the theory says that the maximum value will lie at one of these 5 points. 5 seems like a lot, but compared to everything in this area, 5's really not too bad. So we'll go to the CAS now, and we'll find the points of intersection to get those corner points. Alright, so here is my graph of all of the inequalities. Again, look back at lesson 3 if you want to see where these came from. But that's the picture that I just had on the slide previously. So we want to find our corner points, and I'm just going to draw those on here again for you. So we've got 1 here, 1 here, 1 here, this guy, this one, oh, sorry, I just drew one that's not actually a corner point. Stop and have a think about which one that is. The one that is not a corner point is this one here. Because it doesn't actually go around the feasible region. It just goes around, well, it's beyond that, because the feasible region gets cut along here. So this point here is outside the feasible region. So let's find our points of intersection. I'll start with this one here. So, to do this, you're going to go to Menu, and then you're going to go to Analyze Graph. And we're looking for the intersection. And you can move around so that we can click on the green graph, and I want my second one to be the red graph. So red and green. And now we've seen this sliding line here before. We've got to tell the graph tell the software where to look. So we'll just go in there, and we can see that corner point is the point 2, 3. We'll do the same for this guy here. So once again, menu, 6, 4. Now we're looking for the intersection between blue and red. So the blue graph and the red graph, I'm telling it to look in this area here. The corner point is 3, 1. The other corner points are a little bit easier to find just quickly. Those are there's an x-intercept, a y-intercept, and the point 0, 0. Because these guys are intersections with the axes, with y equals 0 and with x equals 0. So this point here, it's the y-intercept of this line. So the y-intercept here is 0, 4. We want the x-intercept. We want the x-intercept of that line there. The blue one, that's this point down here. The x-intercept of that, if we just solve, that's 10 over 3, comma 0. And then we had 0, comma 8. And this point down here is 0, comma 0. So those are our 5 corner points, found by finding the points of intersection of each of these pairs of inequalities. So here are my corner points: 0, 0, 0, 4, 2, 3, 3, 1, and 3 1/3, which is 10 over 3, comma 0. Which one is best? Well, we want to substitute those points into my objective function, which is 250x plus 100y. So the point 0, 0, when x is 0 and y is 0, well, the whole thing is 0. That makes sense. If I don't make any lesson videos or any example videos, I can't sell them for anything, there's no profit. 0, 4, so I'm making all example videos, no lesson videos. All right, there's a profit there of $400. And we'll try the others. 2, 3, 2 lesson, 3 example gives a profit of 800. 3 lesson, 1 example gives a profit of 850. And 3 1/3, 0, well, that gives a profit of $833. So to maximize this, the best I can do to make the most amount of money possible is this guy here. 3, 1, which means I'm making 3 lesson videos and 1 example to maximize the profits. So that's how we do linear programming. There's 2 examples coming up now. They're both continuations of the examples from lesson 3. I encourage you to have a look and have a try at those, and then watch the videos to see how you do. Just a little extension though, there is another method, which if you're thinking this is enough for now, you can pause the video, you can say, okay, that's enough, but you will see the occasional question on the exams that talk about this method here. So the theory behind this method, which is called the sliding line method of finding an objective function, or finding the maximum value, is we have this objective function, so 250x plus 100y, and we set it equal to 0. So in our example here, we came up with all of these different values for the objective function. If we were to graph each of these, they're parallel lines. So lines that run parallel to one another. And if we were to just animate and move that parallel line, anything that lies along that line is a solution, and we can start to see what's going to give us the best solution, the biggest solution. And just this little key point here, which this is what they sometimes like to ask, is if the objective function, so this guy here, is parallel to one of the constraints, then the optimal solution might actually lie at any point along the line segment. It won't lie just at the corner, but it might lie at this corner, and also anywhere in between. So let's have a quick look at what that looks like on the CAS. So I'll show you a really cool feature here on the CAS that we can use to try and visualize our objective function. So we're going to insert another relation. The relation is going to be the objective function. So 250x plus 100y, but we have to have it equal something. And that something can be a variable, it can be something that changes. As we saw in our example, sometimes it was equal to 0, sometimes it was equal to 100. We got up to, I think, about 850. So it can change. I'm going to set it equal to, and I'm going to pick another random letter. I'm going to choose n for this. So if I say equals n, and then I press enter, you'll see it pops up with this little dialog box asking me if I want to create a slider. Okay, I'm just going to say yes, and we'll see what happens here. So you can see it's come up with this, I'll move it out of the way, a slider value that I can click and drag, and I can slightly move a line around. It's very hard to see right now, but you'll notice something's flashing down in this corner here, because this is telling me 250x plus 100y, which is my objective function, is equal to whatever value I have here. So if I want to change this, I don't want it to go up to 5. I know from what we did with the corner points that I can get up to 850. I'm going to press Control and Menu as I'm sitting over top of that slider, and I'm going to go to Settings. So the variable, again, the n, that's fine. I don't know, we can maybe make it 100 for now. And we want the slider to go from 0 to some largish value. We know, again, we've done this question already, we know that we can get up to 850. So I'm going to make it 1,000. And the step size, you can leave this as automatic if you want. Making it a little bit smaller makes it a little bit easier to see and visualize what's happening, so I'm going to set the step size to 10. Press OK. And now it seems to have colored this weirdly, so I'm just going to quickly change the color to, I don't know, maybe a black line. And you can see down in this corner now that I've got this objective function. 250x plus 100y equals, in this case, 100. And I can click and drag this slider. And as I drag the slider, you'll notice that the line is just sliding. It's shifting across. So going up and down. And at any point along this slider, or at any point along here, these are all of the solutions to where the objective function equals 350. So I can push this n value up. And right about here, I've gotten to where the value of the objective function is 400, and that's at that corner. But I can push further. And we can see there are solutions for 500, 600, 700. Get up to 800 here, but I can keep pushing further and still be within that feasible region. I push to 850, and notice that at this stage I've just gone past that point, and anywhere beyond there, the objective function doesn't intersect with the feasible region. There's no way of doing this with a point that's in this solution polygon in this feasible region. So again, I'll bring that back down, and just at 850, I can see that that's as high as I can get. I'm going through this corner point here. I've already gone through all of the other corner points. That's the only place left, so that's going to be my maximal solution. Like I said, that is a bit of an extension. Come and have a chat with me if you're not sure about what exactly is going on there. But that really is something that is the absolute end. If you're feeling like the rest of this stuff is super easy, at that point we can have a chat. So now we're at the two examples, example 1 and example 2. Have a look at these two examples, and then that's it. So you will have been successful if you can use the corner point method, and I'll just put this in brackets. The sliding point method is kind of optional to find optimal solutions to a linear programming problem. It's time to start practicing, so I suggest you go ahead and do that now.